Welcome back to The Deep Dive, the show that takes complex technical source material and distills it into immediate, actionable knowledge.
Mm.
Have you ever looked at the frontier of AI and thought, that's only for Google and OpenAI?
Mm-hmm.
You are about to have your mind completely changed.
That's absolutely right. Today we are addressing one of the biggest, misconceptions in technology, that building truly sophisticated AI agents that go beyond simple text chat requires a massive capital investment in proprietary licenses or cloud computing credits.
We're diving into how to build highly functional AI agents that can actually see, hear, and create. They are multimodal, and they are free.
The mission for you, the learner, is this. We are distilling the complete, free, and open source ecosystem needed to grant these agents vision, audio, and video capabilities. We're not just listing tools, we're providing the conceptual blueprint for orchestrating them. We're eliminating the need for overly complex coding or those cripplingly high cloud costs.
Right. And the modern requirement for any sophisticated AI agent is multimodality. I mean, think about what a human knowledge worker does. They analyze images, they read scanned PDFs, they listen to meetings, they watch training videos, and they create new visual assets.
Yeah.
Your agent needs to do the same. This deep dive is your shortcut to understanding the specific, specialized engines required for each modality and, crucially, the zero-cost reasoning layer that stitches them all together.
Yeah, exactly. Agents today need to be able to handle complex, real-world input. We're talking messy images, screenshots, multilingual scan documents, high-fidelity audio streams, and continuous video feeds. And they need to do it reliably and, in many cases, privately.
Okay, let's unpack this. The sheer power available through open source to create these agents. We're going to start exactly where the agent's intelligence truly begins, reading the world. That means giving the agent an eye. And that process starts with optical character recognition, or OCR, which, turns raw pixels into usable, searchable text.
Right. When an agent looks at a document, whether it's a photograph of a receipt or a badly scanned legal brief, it just sees an array of pixels. The first fundamental step is turning those disparate pixels into usable structured data. This isn't just about reading text, it's about understanding the context and structure of that text.
And we have two major, powerful open source solutions here, each with a very different specialization and trade-off that you, the listener, need to understand. Let's start with the one designed for pure complexity and structural challenge. PaddleOCR. This is the heavyweight champion of document analysis.
It really is. PaddleOCR, developed by Baidu, is the critical tool for any agent dealing with the messy reality of enterprise data. Its core purpose is to efficiently extract text from the most challenging inputs. So things like low-quality photographs, complex forms, receipts, and poorly scanned PDFs that would choke simpler systems.
And its capabilities really define its power in a professional context. We know it handles low-quality images well. It uses sophisticated image preprocessing baked right in to fix distortions and lighting issues. But the real professional utility, that comes from its advanced structural data extraction, doesn't it? We're talking table extraction and sophisticated layout detection.
That's the key. Think of this scenario. An agent processing invoices. It doesn't just need the list of characters. It needs to know that the string ACME core is the vendor name, that the number in the bottom right corner is the total due, and that the lines of items above are arranged in a table structure, linking specific product names to their quantities and prices. PaddleOCR's layout detection is the foundational intelligence that provides that structured, machine-readable output.
Right. So that structural understanding is what elevates PaddleOCR from a simple text copier to a document intelligence tool. But what about the multilingual support? The source has specifically highlighted Urdu, Arabic, and English. Why is that particularly crucial or, technically difficult?
That's a fantastic question that gets to the heart of the matter. Languages like Urdu and Arabic are not only right to left, which complicates layout parsing, but they also have complex contextual ligatures characters that change shape based on adjacent characters. A simple character recognition model just fails immediately. PaddleOCR has been specifically trained on massive data sets covering these languages. This allows the agent to operate globally, handling complex documentation like WAF notifications, specific legal petitions, or international bank statements where accuracy in non-Latin scripts is just non-negotiable.
So if the task involves structural complexity, multilingual requirements, or messy real-world photos, PaddleOCR is the go-to.
Exactly. Now let's contrast that powerhouse with the lightweight workhorse, Tesseract OCR. Tesseract, originating from HP and now maintained by Google, has been around longer. Its purpose is reliability and speed for, let's say, more straightforward tasks.
Right, Tesseract is what you use when you have clean inputs. It's fast, incredibly straightforward to integrate, and perfect for quick, clean PDF extraction, basic handwriting recognition, and standardized form reading. It really shines when the input quality is already high.
And the use cases reflect this simpler focus. We're talking standardized documents like clean court orders, standardized medical reports, or educational worksheets where the layout is fixed and the text is clear. If you have a stack of, say, 10,000 perfectly legible PDFs that just need the text extracted quickly and efficiently, Tesseract is an excellent choice. It's the foundational tool you rely on when resource efficiency is key and complex layout parsing isn't required. Using PaddleOCR for a simple, clean PDF would be, well, it'd be overkill. Tesseract is the leaner, faster alternative for clean data.
Okay, that makes sense. So once you've extracted the text using one of those tools, the agent often needs to analyze the original image itself for context or to clean it up or to find specific visual markers.
Yeah.
That's where computer vision or CV comes in, right? Starting with the essential toolkit for image manipulation.
The essential toolkit here is OpenCV, the open source computer vision library. You simply cannot build serious vision agents without this library. Its purpose is to pre-process and analyze the raw visual input before you send it off for OCR or, deeper AI analysis.
I like to think of OpenCV as the agent's optical technician, the one who cleans the lens and adjusts the focus. What are we talking about specifically when we say pre-processing?
We're talking about applying algorithms that manipulate the image data itself. For example, detecting edges and shapes is crucial for segmentation, telling the agent exactly where the document ends and the background begins. It handles essential preparation tasks like cropping the document area out of a photo, rotating a skewed scan, and applying filters to remove speckles or noise.
And it's also the tool you use to handle video input, right? Extracting frames cleanly from videos falls under its mandate, preparing those individual images for analysis.
Precisely. And in document analysis, its ability to highlight crucial elements like signatures and stamps is, well, it's transformative for verification agents. You can program the agent to specifically detect the unique shape and color profile of a stamp or a signature. This lets the agent confirm the authenticity or status of a document without needing to read all the content.
The application for that are huge.
Mm-hmm.
Legal document comparison, where you need to check if a specific section changed visually.
Yeah.
Website UI audits, where you identify button shapes and layout elements. And quality inspection agents looking for subtle defects in manufacturing images. So OpenCV is the essential layer that makes the raw visual input usable and targetable for the agent's eventual reasoning model.
And this moves us from static image cleanup to recognizing human interaction, which is a whole different level of vision intelligence. That brings us to MediaPipe.
MediaPipe from Google feels like a massive step up. It provides ready-made, high-level vision pipelines. So instead of building a sophisticated hand-tracking model from scratch, the architecture is just prepackaged.
It is. It's the agent's built-in high-efficiency recognition system, primarily focused on tracking human movement and presence. Its key capabilities include real-time hand tracking, highly accurate face detection, pose estimation, which means recognizing subtle shifts in posture and movement and general object tracking across a scene.
This sounds powerful, but I have a practical question for our listener, the learner. For a fitness agent or a sign language helper, does MediaPipe require a dedicated high-end GPU to track movement in real time? Or can it run efficiently on a basic consumer device?
Yeah.
We are focused on accessibility here.
That's a critical technical constraint to address. MediaPipe is optimized for on-device deployment. That means it can run effectively on mobile phones or standard laptops. While dedicated GPU power always helps, its models are highly quantized and efficient. This efficiency is why it's so powerful for real-time applications. It transforms an agent from a passive reader into an active observer of the physical world. And that allows for those surprising uses you mentioned: fitness agents monitoring form, sign language interpreters translating gestures, and security tools tracking unusual patterns without needing a server farm.
Okay, we've now equipped the agent with eyes to read, clean, and analyze the world around it. We understand documents and human movement. Now we shift gears dramatically. We need to empower the agent to create, to take abstract ideas from a text prompt and manifest them visually with zero license cost.
This is the domain of zero-cost AI artwork, and the core creative engine in the open source stack is, without a doubt, Stable Diffusion.
The purpose is beautifully simple. Generate AI artwork without cost. But the output capabilities cover the entire spectrum of visual needs. We're talking photorealistic images for advertising, design assets like posters and logos, complex 3D artwork, and ready-to-print materials like book covers. It's the ultimate visual utility tool.
And the power of Stable Diffusion lies in its flexibility, which is achieved through the open source ecosystem that surrounds it. The core model is just the beginning. The source material highlights essential platforms like Automatic 111, Comfy UI, and Invoke AI. These are the user interfaces and frameworks that allow you to use critical extensions like control nets for precision composition or specialized checkpoints for specific artistic styles.
We should probably emphasize that running Stable Diffusion locally requires a decent GPU, specifically enough VRAM. We're talking about needing at least, 8 gigabytes of VRAM for decent performance, although highly optimized versions can run with less. It's the highest hardware cost in this entire stack, but the benefit is complete, unfettered, and private creative control.
And that local control enables specialized pipelines that just aren't possible or affordable using cloud APIs. I mean, imagine an agent tasked with creating an entire Islamic book series design where cultural sensitivity and stylistic consistency are paramount across dozens of assets. Or rapid social campaign branding, where the agent needs to generate hundreds of visually cohesive variations in an hour. The ability to control the underlying model, its checkpoints, and its parameters locally is paramount for high-volume, culturally specific creation.
It's the difference between asking an external service for a picture and owning the entire printing press yourself. But once you start dealing with high volume and complexity, simply typing prompts into a text box becomes inefficient. That's where we need an architect for the workflow.
Precisely. The volume and consistency needed for professional use demand more than just the raw generation model. You need a system to chain operations reliably and repeatably. And that brings us to the professional workflow tool, Comfy UI.
Comfy UI is the visual, node-based editor for orchestrating complex Stable Diffusion operations. Visually, it can look intimidating. A tangle of boxes representing processes and lines representing data flow. But fundamentally, it solves the problem of iterative professional design.
This is why it matters for serious creative agents. Simple text to image is fast, but true professional creative work involves multi-step processes. Think of Comfy UI as a modular synthesis chain for sound design. Each node is a separate component. A prompt input, a sampler and upscaler, an in-painting mask, and the lines dictate the data pathway.
So it allows you to build complex pipelines visually. For example, if you need the agent to generate an initial image, then automatically run a detection model to find the main subject. Then apply an in-painting mask to change the background only, then upscale the result. You can design that entire flow once in Comfy UI.
And then you save that workflow. Why is this critical for efficiency and professional content creation? Because it enables crucial features like batch rendering and multi-input workflows without touching complex YAML files or repeating steps manually. If an agent is tasked with designing 50 variations of a book cover, each requiring the same core structure but different text overlays and background details, using Comfy UI's visual reusable workflow ensures efficiency, consistency, and repeatability.
That transition from a single prompt to a repeatable, sophisticated production system, that is what separates hobbyist AI art from scalable commercial application. It transforms the image generation process from a one-off experiment into a professional, systematic production line for things like architectural visualizations, massive poster campaigns, or complex character concept sheets.
Right. It manages the complexity so the agent only needs to feed the initial prompt and the desired output parameters. It leaves the hundreds of intermediate steps, the upscaling, the masking, the refinement, to the automated pipeline.
Okay, so we've covered site and creation. Now we shift modalities again, moving to the auditory realm. For an agent to be truly multimodal, it needs the capacity to process audio, which involves both transcribing speech audio to text, or A2T, and generating it text-to-speech, or T2S. And this domain requires extremely high accuracy and often maximum privacy.
Let's start with the listening component, ATT, beginning with what is, right now, the gold standard for transcription accuracy, Whisper.
Whisper, provided by OpenAI as an open-source model, has been a triumph. Its purpose is to convert audio to text with extremely high precision across diverse domains. It was trained on, 680,000 hours of multilingual labeled audio data from the web. That scales why it's so dominant.
Its massive training data makes its key features incredibly valuable for professional transcription agents. The base accuracy is phenomenal, but it also offers critical features like robust multi-speaker detection. So identifying speaker A versus speaker B, and unparalleled multilingual support, including highly accurate transcription for Urdu, English, and Arabic. For agents analyzing international business calls or complex legal depositions, this capability to parse multiple languages simultaneously and identify the speakers is, well, it's not negotiable.
And the applications highlight the high-stakes value, transcribing court hearings where misinterpretation is catastrophic, medical dictations where precise terminology is required, and generating detailed lecture or podcast transcripts that require timestamping. Whisper has single-handedly lowered the barrier for achieving professional-grade transcription quality for free. But if we're focusing on local processing and privacy, Whisper often needs to run on a server or locally processed via the optimized C++ version. What if the user absolutely cannot, under any circumstances, allow their data to even touch an internet connection?
That's a critical constraint, and one that moves us away from cloud-dependent or even resource-intensive local models to VOSC, the privacy champion.
VOSC's defining purpose is fully offline speech-to-text, or STT, processing. It runs entirely on the local machine and leverages smaller, tailored language models to ensure maximum privacy and minimize latency by avoiding network transfer.
This capability changes the game entirely for sensitive domains, especially those in high-security environments. VOSC is the ideal choice for handling government data, confidential legal audio-like client meetings or internal case reviews, or private academic research where data sovereignty is paramount.
Okay, but does VOSC's accuracy suffer compared to Whisper, given that its models are necessarily much smaller and optimized for local machine use? What's the trade-off the learner needs to know?
That is the core trade-off. VOSC's accuracy, while excellent for many use cases, will generally lag behind Whisper, especially in highly specialized fields or when dealing with thick regional accents or poor audio quality. However, for clear input audio, the difference is often negligible, and the guarantee of total offline operation and zero latency from network transfer far outweighs a slight drop in accuracy in these sensitive domains. It's a choice between maximum accuracy in the cloud or slightly lower accuracy with maximum ironclad privacy locally.
Right, and moving from the agent listening to the agent speaking, we have text-to-speech, T2S.
For T2S generation, the leading open-source options are Piper and Koki TTS. Their primary purpose is generating high-quality, natural-sounding audio from plain text input. They effectively give the agent a voice that is both clear and engaging.
I remember when synthesized voices sounded so robotic. The current generation of these open-source T2S models is remarkable in its naturalness.
Absolutely. The key capabilities here include delivering highly natural voices with appropriate inflection, allowing selection between male and female tones, and crucially, maintaining that multilingual support we see across the OpenStack, including high-quality Urdu and English output.
And how does an agent leverage this? What are the applications?
Well, this stack is fundamental for building accessibility tools, allowing text interfaces to be read aloud for visually impaired users. It also enables agents to generate professional voiceover content for videos, create dynamic audio lessons, or provide audible confirmations for agent actions. It allows an agent to move beyond text output and communicate auditorily, which is essential for comprehensive user experience and a focus on accessibility.
We've covered site creation and sound. Now we move to the most resource-intensive and complex modality, video. Video agents need to analyze existing footage and also generate new moving content.
Video is the ultimate challenge because it combines image processing, audio analysis, motion tracking, and temporal reasoning. It requires immense computational overhead just to break the video down into constituent parts before any AI analysis can even begin. So we need a fundamental processing layer that can handle that initial burden.
And that foundational layer is FFmpeg, which is truly the Swiss Army knife of video processing. Its purpose is the fundamental, free processing, manipulation, and conversion of video and audio files.
Every serious video agent pipeline starts with FFmpeg. I cannot overstate its importance. Its capabilities are the unsung heroes of video analysis. Extracting individual frames at set intervals, converting between dozens of video formats for compatibility, clipping and trimming specific sections, and critical tasks like noise removal from the audio track embedded in the video stream.
When an agent is dealing with raw security footage, for instance, it's not going to feed a 2 GB file directly to an LLM. It needs FFmpeg to break that down.
Exactly. The process is typically use FFmpeg to extract one frame every second, then pass those 60 frames to the vision pipeline for analysis. You're minimizing the computational load by, 99%? The uses demonstrate this foundational role. CCTV analysis requires clean frame extraction. Lecture content extraction involves trimming, formatting, and re-encoding for web delivery. And general podcast refinement often starts here for format conversion or merging different audio and video tracks. It is the mandatory, non-negotiable step before any deep learning model touches the data. And once the video is prepped by FFmpeg, we apply the vision tools we discussed earlier, specifically OpenCV for video. Here, the purpose is applying computer vision principles frame by frame across the video stream to generate meaningful metadata.
This is where we move the analysis from static images to dynamic temporal content.
Precisely. OpenCV allows for high-level capabilities applied continuously. So, object detection throughout a scene, identifying specific items or people frame by frame. Scene segmentation, identifying exactly when the camera cuts to a new shot. And precise, long-duration motion tracking for security or behavioral analysis.
The impact here is monumental. Think security agents monitoring a perimeter where the agent needs to track an anomaly over 3 hours of footage and summarize the path of the object. Or classroom monitoring for specific student behaviors, or inventory audits where the agent needs to track movement of items through a warehouse on video. OpenCV provides the agent with the temporal context it needs to understand change over time.
And finally, the creative side of video, which, while resource-intensive, is becoming rapidly accessible through free tiers and open models.
Right, the free tier options here allow agents to quickly mock up dynamic content without massive render farms. Pika Labs is focused on generating short, AI-powered videos.
Pika Labs excels at creating short-form, impactful clips. These short clips are perfect for rapid use cases like generating YouTube motion graphics intros or outros, quick storytelling previews for social media campaigns, or generating marketing teasers that immediate visual impact without a massive production budget.
They often work by leveraging existing static images or simple text prompts and just injecting movement. It's rapid prototyping for motion.
And then we have Runway ML, which has cemented its place as a leader, offering not just AI video generation, but also strong editing and manipulation capabilities.
Runway ML goes a step further than Pika, allowing for more complex tasks like scene creation based on text, sophisticated background replacement in existing footage, and generating detailed AI animations that adhere to specific artistic constraints.
The key takeaway for the learner here is that even the free tiers offered by these platforms, which usually involve credit limits or watermarks, provide enough creative fuel for agents to rapidly prototype and test visual concepts. These tools grant the agent powerful creative control over the moving image, making them capable of generating entire multimedia campaigns from a single text prompt.
Okay, so if we connect this to the bigger picture.
Yes. You can see that the tools we've outlined, the individual engines for sight, sound, and creation, are incredibly powerful in isolation. But the true utility, the magic that builds a truly intelligent AI agent, happens when these independent tools are systematically orchestrated by a central reasoning engine. In almost all modern, sophisticated workflows, that orchestrator is ChatGPT or another powerful large language model, an LLM.
This is where we move from a toolbox to a fully functional, highly intelligent system. The LLM's role is not to process the image or the audio itself. It's to reason, plan, and issue commands to the specialized tools. It does this primarily using function calling, right? Where the LLM writes specific instructions, often as a JSON object, that tell the external tool exactly what to do and what format the response should be in.
This is the conceptual climax of the deep dive. The LLM acts as the central brain, leveraging the specialized muscles, PaddleOCR for vision, Whisper for audio, and so on, to execute complex tasks. Let's walk through some of the most powerful workflow combinations outlined in the source material.
We'll start with the classic document analysis engine that can replace junior staff in a high-stakes environment. Vision plus OCR plus ChatGPT.
Imagine the scenario. A law firm receives 50,000 pages of discovery overnight. It includes handwritten notes, low-quality faxes, and complex spreadsheets. The agent must process this immediately.
So the workflow begins. The raw image or scanned document is first processed by the powerful structural engine, PaddleOCR. The LLM sends a JSON request to the PaddleOCR module with the image path and expects structured JSON output back, not just raw text. And this structured output contains the text, the layout coordinates, and the table relationships.
Second, the extracted structural text and metadata are fed directly to ChatGPT. This is where the reasoning happens. Third, ChatGPT acts on this structured data. It summarizes the contract clauses, compares the data against a standard legal template, detects specific issues like missing signatures or contradictory language, and then generates a formal priority-ranked report.
So the agent acts as a hyper-efficient paralegal. The applications are massive. legal document verification, high-speed contract analysis, and rapid receipt categorization and compliance checking for financial audits. It turns physical paperwork into actionable digital intelligence at scale.
Next, consider the auditory analysis pipeline, where the agent becomes an expert listener and summarizer. Audio plus whisper plus ChatGPT.
So the input, a 2-hour court recording or a board meeting, is processed by the highly accurate whisper model. The LLM issues a command to whisper, requesting the full transcript and, crucially, multi-speaker identification.
The resulting detailed transcript is then fed to ChatGPT. ChatGPT digests this massive volume of text and then performs high-level reasoning. It can produce precise summaries, identify key questions raised by specific speakers, extract all action items and assign follow-up tasks, or even flag moments of high emotional tension if the transcript includes that metadata.
This is indispensable for addressing information overload. It's analyzing long court recordings, synthesizing the key takeaways of crucial business meetings, or breaking down long sermons or lectures into key concepts and actionable insights. It's filtering dense audio streams into prioritized, categorized information.
Exactly. And now for video analysis, the most complex synthesis: video plus FFmpeg plus OpenCV plus ChatGPT.
This starts with the raw video being processed by FFmpeg. The LLM instructs FFmpeg via a JSON function call to extract one frame every 5 seconds. The LLM then commands OpenCV to analyze those, 1,200 extracted frames, identifying specific objects, tracking motion, and detecting scene changes.
The output of the vision tools is pure metadata, a textual report. Scene change at 01.15.300. Object red car detected exiting frame right at 01.16.05. This report is then fed to ChatGPT. ChatGPT summarizes the video content based purely on this process metadata. It never has to process the video data itself. It reads the detailed report generated by the vision tools.
The applications for that range from high-stakes security analysis, where the agent summarizes 24 hours of CCTV footage into a 5-minute narrative report detailing every anomaly, to creating detailed lecture summary based on slide changes and presenter movements, or evidence extraction from video footage for legal review. It provides a synthesized understanding of complex visual events.
And finally, the creative feedback loop that produces iterative designers. Image Gen plus ChatGPT.
First, ChatGPT acts as the creative director. It writes the detailed design brief, the prompt for the artwork. It might specify style, color, aspect ratio, and composition elements, often based on a user's abstract input like, "I need a cover for a space opera novel." The LLM generates the initial prompt in a structured format suitable for the image generator.
Second, Stable Diffusion or Comfy UI generates the image based on that detailed brief. Crucially, the loop closes when the user provides feedback. The color is too dark and the astronaut needs to look more heroic. That feedback is then fed back to ChatGPT, which acts as the refining editor. It refines the original design brief to iterate the image, often leveraging the complex, multi-step pipelines orchestrated in Comfy UI for precision adjustments like inpainting or style transfer.
This orchestration ability elevates the generation tools to true design partners. It drives sophisticated applications like automated book cover pipelines that adapt based on user feedback, generating entire cohesive branding systems, or running massive poster campaigns where hundreds of visually consistent assets are needed quickly. Everything we've discussed so far demonstrates the immense power of the open source stack and how ChatGPT can orchestrate it. For many critical applications, especially legal, governmental, and medical, the idea of sending sensitive data to the cloud is absolutely prohibited. Which brings us to the crucial topic of total privacy and building the entire powerful system on your own hardware.
This is where the cost and privacy equation collapses to zero. By building agents entirely locally, running behind your own firewall, you eliminate recurring cloud costs and ensure complete ironclad data sovereignty. This is the domain of self-hosted AI.
The core of any agent is the large language model, the LLM, that handles the reasoning and orchestration, the brain we just discussed. For the local stack, the primary hub is Llama.
Llama's purpose is to allow you to run leading multimodal LLMs entirely on local hardware, your laptop, your private server, or a corporate machine. It handles the complexities of downloading, optimizing, or quantizing and serving the models. The benefits are massive for high-stakes users: zero cloud cost, total privacy, and the ability to work completely offline.
And what makes it so accessible now is the optimization of these large models. Models that once required hundreds of gigabytes of VRAM can now run efficiently on consumer-grade hardware, thanks to formats like GGUF and quantization techniques.
Exactly. This is why Llama is ideal for specific, highly regulated users. Law firms processing confidential client discovery data, government lawyers handling sensitive files, and research institutions dealing with proprietary data sets. The fact that the reasoning engine never leaves their controlled infrastructure is the defining feature.
And complementing Llama, we have LM Studio. While Llama focuses on running the engine itself, LM Studio provides the user interface and development environment.
Right. LM Studio's purpose is to run LLMs, manage embeddings, and enable ARIA, retrieval, augmented generation, all within a user-friendly graphical interface, a GUI.
Wait, ARIA is a key concept here. Since we are building agents that handle long-term knowledge, we need to clarify this for the learner. What exactly is ARIA, and why is it essential for a local agent?
Orgo, retrieval augmented generation, is essential because LLMs have a knowledge cutoff. They only know what they were trained on, and a limited working memory, or context window. Argy solves this by giving the LLM an external library or a permanent long-term memory system. So when the user asks a question, the Argy system retrieves relevant information like specific paragraphs from a private PDF database and feeds that information alongside the user's prompt to the LLM.
So Argy allows the agent to reason over private, current, or proprietary information that it never saw during its initial training.
Precisely. And that requires a structured memory system, which is where LM Studio helps. It facilitates things like simple drag-and-drop PDF reading for local ingestion, local chat interfaces for interaction, and native support for local voice and image inputs. It democratizes the ability to set up Orgy systems on consumer hardware. And that memory system, the library itself, is handled by a vector database.
So the vector database, like Chroma or ACS, which we'll discuss in the full stack acts as the sophisticated librarian, indexing every chunk of proprietary data the agent needs to reference. It doesn't store the original file, it stores a numerical representation, or embedding, that allows the RAG system to find the most conceptually relevant information instantly.
This leads us to the complete, self-contained, fully private AI agent architecture.
So we can detail the 6 fundamental components needed to create fully private AI agents using only open source or local tools. This is the blueprint for zero cloud reliance.
First, you need the brain, the orchestrator. A llama running the optimized LLMs for reasoning and orchestration. You might run a quantized version of Llama 3 or Mistral.
Second, the dedicated, efficient local audio processor, Whisper.cpp. Why the C++ version specifically?
Because it's highly optimized for speed and low memory footprint on local hardware. It ensures quick, private transcription without hogging resources.
All right, third, the dedicated local visual text reader, Tesseract, the lightweight OCR. For local private document handling, Tesseract is the reliable and fast OCR solution for turning those scanned documents into text without any network call.
Fourth, the creative engine that doesn't require the internet. Stable diffusion running locally on the GPU. You generate images and visual assets entirely behind your firewall.
Fifth, the memory and long-term knowledge base, the RAG components. Chroma, or FAIs, serve as the vector databases, acting as the librarian and long-term memory bank, storing and retrieving context for the LLM.
And finally, sixth, the user interface. Streamlit, which allows for a clean, Python-based, web-style front-end for the user to interact with the agent without needing complex web development or heavy deployment infrastructure.
And that combination creates fully private AI agents capable of handling every modality we've discussed: sight, sound, creation, and deep reasoning, entirely behind a firewall, with zero subscription costs. The main constraint here is GPU VRAM, particularly for the stable diffusion and larger LLM components, which typically requires a dedicated machine. But it's still cheaper than the recurring cloud costs over time.
Absolutely.
So we've mapped out the tools and even built a complete, highly private, multimodal open source agent conceptually. The practical question remains, once built, how do these complex agents get distributed and used by their intended audience?
Deployment depends entirely on the agent's purpose, scale, and, critically, its security requirements. The source material outlines 3 primary deployment models that define the environment the agent lives in, starting with the most accessible. Browser-based agents. These are generally agents designed for public access, sharing, or quick demonstration. The primary benefit is zero friction for the end user.
We're talking about platforms that provide instant accessibility. Hugging Face Spaces is the standard way to share experimental or demonstration models, often including models built with Streamlit or Gradio. Streamlit Cloud allows you to host those custom UIs we just mentioned easily for internal teams or a controlled public audience. And Vercel is excellent for hosting fast serverless web applications that utilize API calls to a robust back-end infrastructure, which might host the actual LLM and multimodal modules. These models prioritize ease of access and shareability above all else.
Next, we have mobile multimodal agents. This requires a specific hybrid architecture to leverage the processing power of a phone while maintaining complex multimodal capabilities.
The architecture generally uses React Native or similar cross-platform frameworks for the front end, allowing the agent to run on both iOS and Android. For high-level reasoning, it often leverages the ChatGPT API for the back-end intelligence, as running large LLMs on mobile processors is still challenging.
But here's the key technical point. They embed open source vision and audio tools, such as local versions of OpenCV or Whisper, directly onto the device. This is crucial for latency. The agent can handle real-time tasks, processing a photo taken by the phone's camera for vision, or listening to dictation for audio directly on the device, before sending only the small processed metadata or transcript to the cloud LLM for reasoning. This dramatically speeds up response time and saves bandwidth.
And finally, the most robust, secure, and resource-intensive model, enterprise multimodal agents. These are built for high scale, maximum security, and intense data throughput within a large organization.
This deployment requires complete control. It means self-hosted pipelines, dedicated, often expensive, GPU servers running 247 on-premise to handle the processing load of concurrent users and massive data volumes. They absolutely require on-premise RGI systems, the memory is stored locally, and absolute integration with existing organizational infrastructure, often via SSO or single sign-on integration for seamless, secure user access. These are the highly customized secure agents built for large corporations or government entities where internal control and compliance are paramount and complexity is expected.
This has been an incredibly detailed and necessary mapping of the modern open source AI ecosystem. We have moved far past the idea that powerful AI agents are locked behind massive corporate paywalls. The tools are here, they are free, and they cover every sensory modality an agent needs.
Absolutely. When you look at the sheer diversity and power of this free stack, from PaddleOCR structurally reading complex contracts to Vosk handling private audio and Alama providing local reasoning, the toolset is comprehensive and mature.
Let's quickly recap the specific types of agents the listener can now conceptually build, based purely on this free and open source foundation.
You can build sophisticated legal document analyzers that categorize petitions and extract clauses with structural intelligence. Health report explainers that can transcribe medical dictation and summarize complex findings with full privacy. Highly automated multimedia content creators that manage complex image and video pipelines using Comfy UI. Robust business intelligence agents that pull structured data from receipts and invoices. Specialized educational systems for personalized content generation. And, critically, government-grade private AI agents that meet stringent security requirements by operating entirely locally.
The source material confirms that the barrier to entry for building sophisticated multimodal AI is no longer capital or proprietary access, but simply knowledge of orchestration. How to connect Whisper to Alama and Alama to PaddleOCR. This raises an important question. Now that the tools are free, accessible, and completely modular, which societal problem will you choose to solve first?